So, hi everyone, I'm Róbert Trényi, and first of all, I would like to thank you for the opportunity to be able to present our work in this conference, which is about the asymptotic performance of a quite famous QKD protocol, the coherent-one-way protocol. And this is based on these two papers. So let me start by explaining why there is the cow protocol interesting. So the main difficulty with quantum key distribution protocols is the fact that high quality and high performance single photon sources are really challenging to realize. So in reality, basically dim laser pulses are used which emit phase randomized weak coherent pulses. Basically, this means emitting the state of the following form, and we can see that sometimes it happens that 2, 3, or more photons are emitted, and this is problematic because it opens up the possibility for the photon number splitting attack, which means basically that Eve is performing quantum non-demolition measurement on the pulses, and whenever she finds more than one photons in a pulse, then she just splits one off for herself that carries the same information that goes to Bob, and basically she makes use of this information when, for example, Bob announces the basis information. And just to give an example that this is actually a serious limitation, we know that the BB84 protocol with weak coherent passes basically has a pretty bad scaling that scales quadratically with the system's transmittance, and this is pretty bad because originally with single photons it scales linearly. So we have to come up with solutions to rule out the possibility of this attack, obviously. So probably the most known solution is the so-called decoy state quantum key distribution, where the parties use different intensity settings for their weak coherent passes that they choose randomly, and for example only one of them is used for key generation. The others are just there to basically be able to detect Eve or bound the multiphoton components, in other words. And well, the main point here is that with this method, the linear scaling in the system's transmittance is achievable. Another solution is the strong reference pulse technique, which is based on the B92 protocol, and it can also achieve a linear scaling with the system's transmittance. However, it requires really high quality detectors. And in this regard, it is also important to note that this linear scaling in eta is basically the best possible asymptotic scaling due to the repeaterless bound for point-to-point QKD. And as a third option, I would like to mention the distributed phase reference QKD protocols. It has basically two subgroups, the differential phase shift and the coherent one-way or cow protocols. I will introduce these in the next slide in more detail. But these protocols basically have in common that they have relatively simple experimental implementations, and they make use of coherence either in the encoding or monitoring side, but their security was not fully established. Okay, so now let us look at these subgroups in a bit more detail. So for the differential phase shift QKD, basically encoding is done by encoding information in the phase difference between coherent pulses. It can be shown that it can achieve slightly better scaling than the quadratic, but it is also important to note that there are improved versions of this protocol, for example, the round-robin DPS QKD, where basically coherence can be checked between randomly chosen coherent passes, not just subsequent ones. And with this technique, the linear scaling can almost be reached. However, it comes at the price of making the implementation a bit more complex. So now let us focus on the main concern of this presentation, the cow protocol, where basically encoding is done by combining coherent or vacuum passes. I will introduce the protocol in more detail in the next slides. The main point here is that security, the security of the cow protocol was not fully established prior to our work that are cited on the first slide. Only upper and lower bounds were known to, and one can see that there was a gap between the known lower and upper bound on the secret key rate of this protocol, and also there were bounds against restricted type of collective attacks that scaled with linearly with the system's transmittance. And it was known that for some protocols, general and collective attacks are basically equivalent in the case of infinite number of sent signals. So it was really hoped that this linear scaling was the true scaling of this protocol, which will turn out that it's not actually. But this could be the reason why, without having fully characterized security status, this protocol was already or is already commercialized, and the long distance experiments have been performed using this protocol, and these experiments basically cover more than 300 kilometers. So now let me introduce the cow protocol briefly. Basically, Alice encodes information in a combination of coherent passes and vacuum passes. And she also uses decoy states to be able to detect for eavesdropping. And already at this point, I want to emphasize that whenever I say pass, I mean one out of these two. And whenever I say signal, I mean the combination of these two pulses. So Bob measures these sent signals in his data line. Basically, he measures the time of arrival of the coherent passes and reports back to Alice if he got a click, without revealing which time slot the first or the second was it. And then Alice discloses the information of whether it was a key generation signal or a decoy signal, and they use only the key generation rounds to form the secret key. And Bob also has a monitoring line, as we can see here, which is basically a Mach-Zehnder interferometer, where he's able to check the coherence between two subsequent coherent pulses, like for example these two. This monitoring line is designed such that if for two subsequent coherent passes, this detector by design will never click. So basically, in this protocol, two quantities are monitored, one of which is the QBER, the quantum bit error rate, which is the probability that Bob misidentifies a key generation signal. And regarding the monitoring line, we can introduce the following visibilities. Basically, this is the conditional probability that the DM1 detector clicks, given that the S sequence was sent by Alice, and the same for the DM2 detector. And we can see that these signal combinations are all the combinations where we have two subsequent coherent passes. So under normal operation, when there is no eavesdropping, no errors, everything is ideal, then by design this PDM2 quantity is 0, which makes the visibilities for all S to equal 1. And also I would like to introduce another important quantity, which is the gain, which is the probability that Bob observes a detection event in his data line percent signal. And already at this point I would like to mention that we will show in the following slides that its asymptotic secret key rate scales at most quadratically with the system's transmittance. Okay, so before going into the details of our attack that we used to obtain the previous upper bound, let us highlight the weak points or the attackable points of this protocol. So first of all, these signal states are linearly independent, as we can see it from these calculated inner products, which means that unambiguous state discrimination is possible for Eve. Of course, for this, Eve has to allow for having inconclusive results sometimes, and this needs to have a higher value than the certain threshold value. But this way, basically, Eve can avoid misidentifying the signal states. And the other weak point is that vacuum pulses are included in the signal states, which inherently break the coherence between signals. In what follows, I will give an example. What do I mean by this? But this is an important point for Eve to have a perfect values for the previously mentioned visibilities. So now let us look at the so-called sequential attack against this protocol. So basically Eve measures out every signal one by one using an unambiguous state discrimination strategy, and we can see basically the constraints that she poses on her POVM elements. So here we have the emitting probabilities of Alice's different signals. The POVM element 0, 1, 2 corresponds to identifying the 0, 1, or 2 signal, and E3 corresponds to having an inconclusive result. And these are the constraints that Eve requires. We can see that she requires to be in the unambiguous state discrimination regime, as we have zeros here. So basically, the process for her to determine what measurement she needs to perform is that for a given f and alpha, f which is the emitting probability for a decoy state, and alpha is the amplitude of the coherent passes, she basically tries to maximize the probability PC to have a conclusive result in each measurement. And surprisingly, this can be done analytically, but now I don't want to go into the details of the formula. So with this attack, whenever she obtains inconclusive results, in order to avoid introducing errors, the eavesdropper Eve resends vacuum signals, because she doesn't know anything about that particular signal. And she tries to collect as many consecutive conclusive results as possible. Let me remind you that whenever it's a conclusive result, it is the actual signal, since we are in the unambiguous state discrimination regime. And based on these results, she does some post-processing, and she prepares new signal states based on these results, of course, and resends them to Bob via a lossless channel. And it is important to point out that this attack is an intersend resend type of attack, which transforms the channel into an entanglement breaking channel, which means that the parties cannot distill a secret key if this attack is performed. So if the statistics that Eve provides with her attack is compatible with the statistics that the parties measure, then it means that the protocol is actually insecure. Okay, so the path processing that Eve does on consecutive conclusive results is basically that she only resends blocks or subblocks that are bordered by vacuum pulses. Let me just illustrate this with an example. Imagine that Alice sends this sequence of signals. Eve measures this, so she got a conclusive consecutive results here in this block. And if we look at the pulse structure, we see this. And according to this algorithm, she basically keeps only this part, which is the largest possible block that is located between vacuum pulses, and she replaces this coherent pulse by vacuum. So she only resends these 1D signals. So why is this necessary? Let's imagine the situation where Eve basically resends also blocks like in this red rectangle, which has non-vacuum pulses on its ends. So here we can see that here Eve got a right result, and here she got an inconclusive result, which is reflected in the pulse structure like this. So what Alice sent is basically two subsequent coherent pulses. So the DM2 detector, as we recall from earlier, would never click in this case. But if she resent this block, then she would remove this coherent pulse because she got an inconclusive result. So in this case, if the parties check the coherence between these two signals, it is possible that the DM2 detector clicks. So Eve basically is breaking the coherence between two subsequent coherent pulses. So it means that Eve could be in principle detected. So to sum up the attack, basically the unambiguous state discrimination makes it possible to have the Q bear 0 because Eve never misidentifies state, and with her post-processing strategy she also avoids breaking the coherence on the borders of the blocks that she resends, so she can also have visibility 1 values. So these are the perfect values for the monitored quantities, and this is why our attack is a zero error attack. So now let me explain how this attack can be converted into an upper bound on the secret key rate. So we follow the process of the attack. Given the protocol parameters, Eve determines the optimal unambiguous state discrimination. She gets an optimal value for having an inconclusive result, and from this we can calculate G0, which is basically a threshold value for the gain, and this means that below this gain value Eve can achieve Q bear 0 and visibility 1 values, so the perfect values for the monitored quantities. And this means that any experiment below that gain value is insecure given these parameters. And this is so because in an experiment it's never possible to reach these perfect values, while Eve can mimic these values with her attack. And since it's an entanglement breaking channel, the parties cannot distill a secret key, so their experiment is actually insecure. So this also means that given the values of f and alpha, there is a maximum value for the distance between the parties in the experiment, or a minimum value for the system's transmittance, such that this inequality doesn't hold, which means that the experiment is actually safe from this attack. Or to put it differently, for a given value of f, and for every value of the system's transmittance or distance, there exists a maximum allowable value for the amplitude of the coherent pulses such that this threshold G0 value is just smaller than the gain value of the experiment, and knowing its experimental parameters. And this condition is, as we explained before, this is the condition to be safe for an experiment to be safe from our zero error attack. Intuitively, this can be explained as follows. So if alpha, or in other words, the intensity of the coherent pulse is too large, then as we saw the inner products of the signal states, they become more orthogonal, which means the unambiguous state discrimination easier for Eve, and which means that she gets inconclusive results with a lower probability, and this makes G0 too large. And so if it happens to be larger than the G value of a certain experiment, then it basically makes it insecure. So determining the alpha max value for every eta, we can just plug this into this trivial upper bound on the secret key rate of the cow protocol. This quantity is basically the probability that Alice emits a signal that encodes the bit value 0 or 1, and that it causes a click in the data line. This is a trivial upper bound for that. So we plotted this trivial upper bound as a function of the system's transmittance, and we can see that it is parallel to the line representing the quadratic scaling, which means that we found an upper bound that scales quadratically with the system's transmittance asymptotically. We also give an example for an experiment with the realistic values. So for example, the intensity of the pulses is 0.5, which is the typical value for decoy state protocols. The F value is 0.1, and all of these values are taken from real life experiments, and we calculated after what distance this experiment becomes insecure, and we found that only after about 20 kilometers with these values the cow protocol becomes insecure, basically. And we also showed in the paper that actually all the implementations of this protocol in scientific literature are insecure. So to conclude, we basically saw that the asymptotic secret key rate scaling of this popular cow protocol is quadratic in the system's transmittance, which makes it inappropriate for long distance quantum key distribution. And this protocol also serves as an example where coherent attacks can actually be more powerful than collective attacks. And also that to achieve the hoped linear scaling of this scheme, the scheme has to be modified somehow. We have more possibilities for that, so maybe we can monitor more quantities, not just the visibilities and the QBER, or we can check coherence between non-adjacent coherent passes as well, like in the round-robin DPS QKD, or we can make USD, the unambiguous state discrimination measurement, more difficult for Eve by adding extra states to the signal states. Whatever solution we choose, basically we will end up with a protocol that has a less simple or more complicated implementation. With this, I would like to thank you for watching this video, and I'm looking forward to your questions. Thank you.